Okay, guys. So last week we did derivatives and some rules like the product rule, quotient rule, and most importantly, the chain rule. Okay. So here is a review of what we have done so far. So last week we have studied derivatives of functions. So here is a small table that we can make. This is f of x. And next to f of x, I'm going to write the derivative f prime of x. Like x to the power n. F prime is n times x to the power n minus 1. For f of x equal to sine x, f prime is cos x. For cosine x, f prime is minus sine x. For tangent of x, f prime is 1 plus tangent square of x. And this is equal to secant square. And we also we studied exponential e to the power x. The derivative is e to the power x and the derivative of ln of x is 1 over x. So these are some basic elementary functions and their derivatives. As I said, one of the most important rules or formulas for derivatives is the chain rule. The chain rule says that if u is a function, if u is a function of x, so u can be anything like x squared, sine x, anything. Then the derivative of fu, f of u, and f is another function, is equal to u prime times f prime of u. So this is the chain rule. In particular, if I want to use the chain rule for these elementary functions, then we have these new formulas. So the derivative of, for example, u to the power n is equal to n u prime u to the power n minus 1. The derivative of sine of u is u prime cos u. The derivative of cos u is minus u prime sine u. The derivative of tangent of u is u prime times 1 plus tangent square of u. The derivative of e to the power u is u prime e to the power u. And lastly, the derivative of ln of u is u prime divided by u. So here is the chain rule when it is applied to this elementary function. So instead here for these functions, instead of f, I have like x to the n, sine, cosine, tangent, e to the x, and ln. Okay? Is that clear for everyone? Okay, so today I'm going to discuss how to sketch graphs of functions using derivative, first derivative and the second derivative. Okay, so this is a new topic, how to sketching graphs of function. For that purpose, so we need to know sometimes the limits of the function at infinity. Because whenever you want to sketch the graph of function, it's very important to know the limits at infinity, or more general, the horizontal asymptote. So the limit at infinity is related to the horizontal asymptote. And we also need to know the vertical asymptotes. So I think you know the vertical asymptote, what a vertical asymptote is. So now I'm going to discuss the horizontal asymptote, which is related to limits at infinity. So we have some functions like x, if n is a positive integer, so if n is positive, then we know that the limit of x to the n when x goes to infinity is infinity. If n is positive, like, for example, x squared, x cubed, even root x. When x goes to infinity, the limit is infinity. So there is no horizontal asymptote for this guy. Also for e to the power x, I know that the limit of e to the power x, x goes to positive infinity, again, is infinity. So here, again, because the limit as infinity is infinity, no horizontal asymptote. And the same for logarithm. Logarithm, limit of ln of x, x goes to positive infinity, is again infinity. So no asymptote. But for some function like 1 over x, so the limit of 1 over x, x goes to either plus or minus infinity, is 0. Or limit of e to the power x when x goes to minus infinity is 0. Or in general, the limit of 1 over x to the power n, x goes to infinity, either plus or minus, is 0 if n is positive. Whenever the limit at infinity is a number, could be 0, it could be 1, any number, then that number is a horizontal asymptote. So here is the definition of horizontal asymptote. Let me write it down. So horizontal asymptote. So we say that if limit of f of x, x goes to either plus or minus infinity, is some number L, is finite. So it's a finite number. Finite number means it's not infinity, it's some number. Then y equal to L is a horizontal asymptote. So for example, y equal to 0 is a horizontal asymptote for 1 over x. You see, this is I'm going to draw 1 over x, the graph of 1 over x, it looks like this. So you see when x goes to infinity, y equal to 0, this line, the x-axis is y equal to 0, right? This line, the x-axis is y equal to 0. It's a horizontal asymptote. Or for this function, when x goes to negative infinity, e to the power x. So e to the power x, let me draw this graph. So here is the graph of e to the power x. Y equal to x. Again, you see, y equal to 0 is a horizontal asymptote. Because when x goes to negative infinity, this function goes to 0. Negative infinity, it goes to 0. It's also good to know e to the power negative x. E to the power negative x, it looks like this. This blue one. Y is e to the power negative x. So for e to the power negative x, when x goes to positive infinity, the limit is 0. Right? So y equal to 0 is also an asymptote of e to the power negative x. Because this guy, when x goes to infinity, is 0. So far, so good. Any question? So this is the definition of horizontal asymptote. Also recall the definition of the vertical asymptote. So what was the vertical asymptote? So I'm going to write it here, vertical asymptote. Vertical asymptote. It's like this. If limit of f of x, x goes to a, is either plus or minus infinity, a is a number. A is a number. Then x equal to a is a vertical asymptote. So if limit of f of x, x goes to some number like a is infinity, it could be plus or minus infinity, then x equal to a, because x equal to a is a vertical line, is a vertical asymptote. So look at the difference between the horizontal and vertical asymptote. The difference is that here, x goes to infinity for horizontal, x goes to infinity, but y is some number, L, okay? X goes to infinity, y is a number. For vertical asymptote, x goes to some number, y is equal to infinity. So you switch the role of x and y, right? So this is vertical versus horizontal asymptotes. For example, f of x equal to ln of x, the natural logarithm. If x goes to limit of ln of x, x goes to 0 plus is minus infinity. So when x goes to 0, ln is minus infinity. I can draw a picture of ln so that you see. So this is ln of x. So this is y equal to ln of x. You see when x goes to 0, of course, from the right-hand side, because the domain of ln is positive number. So when x goes to 0, approaches 0, y goes to negative infinity. So x equal to 0 is a vertical asymptote for ln. So these are important points and facts about vertical and horizontal asymptotes that you should know. It's very helpful, in particular, when you want to draw or sketch a graph of a function. Obviously. Okay, now let me talk about how to draw in general, how to use derivative to draw the graph of a function. So I begin by looking at an example. So the example we're going to study is y equal to e to the power minus x squared. So please listen carefully. These are very important. So I want to show you how finding derivative, first derivative and second derivative can help us sketching the graph. So what is y prime? So the first derivative. I compute the first derivative. Y prime is, so here is e to the power u. Remember that the derivative of e to the power u is equal to u prime e to the power u. So the derivative of e to the minus x squared is minus x squared prime e to the power minus x squared, which is equal to minus 2x e to the power minus x squared. So here you can see that when x equal to 0, so if x equal to 0, then y prime is equal to 0. That means at x equal to 0, you have a horizontal tangent line. Because at x equal to 0, y prime is equal to 0. What about the second derivative? So y double prime is, the second derivative is, so the derivative of this guy. So the derivative of minus 2x e to the power minus x squared prime. So here I need to use the quotient rule, right? The quotient rule. What is the quotient rule? The quotient rule says that the derivative of the not the quotient, the product rule. The product rule says that the derivative of the product is that the derivative of the first one, which is minus 2x. What is the derivative of minus 2x? The derivative of minus 2x, minus 2 times the second function times e to the power minus x squared plus the derivative of the second function. But I know the derivative of this because I just have it here. The derivative of e to the minus x squared is minus 2x e to the power minus x squared times the first function. So you have minus 2x times minus 2x e to the power minus x squared. So y double prime is equal to minus 2 e to the power minus x squared plus 4x squared e to the power minus x squared. Here you can factor out 2 times e to the power minus x squared times, you have minus 1 plus 2x squared. So y double prime is equal to 2 times e to the power minus x squared times 2x squared minus 1. So it's useful, as we will see very soon, to find the point at which the second derivative is 0. So you see y double prime is 0 if and only if, so 2x squared minus 1 is 0. But for what values of x 2x squared minus 1 is 0? If x is square root of plus or minus square root of 1/2. Right? So if x is plus minus square root of 1/2, this guy becomes 0. So the whole thing, which is y double prime, would be 0. Okay. So these are all we need for y prime, y double prime. And here I will show you how we can use them in order to study the graph of the function. So to study the graph of a function, you need to make a table like this. Table. So the first row, you put the values of x at which either y prime or y double prime is 0. So here I list all the values where either y prime is 0 or y double prime. So you see, when x equal to 0, y prime is 0. When x equal to plus minus root 1/2, y double prime is 0. So we have 3 important numbers that are 0 plus minus square root of 1/2. So I put them in order. So the smallest one is minus root 1/2. The second one 0, and the last one plus root 1/2. So these are the x values. Now I have f prime. I put f double prime here, and here f. So you see, you make this table. So when x is 0, f prime is 0. So at this point, f prime is 0. It's important to know when f prime is positive and when f prime is negative. So what is f prime? F prime is minus 2x times e to the power minus x squared. E to the power whatever, when you have e to the power something, that is always positive. So you don't need to worry about this. So the sign of f prime only depends on minus 2x. Okay? So that means if x is positive, f prime would be negative, right? If x is positive, f prime would be negative. If x is negative, f prime would be positive. So that is the sign of f prime. I will tell you why this is important. Now look at f double prime. f double prime is 2x squared minus 1 times 2 times e to the power minus x squared. Again, exponential is positive always. So forget about it. Just look at the 2x squared minus 1. So 2x squared minus 1 is 0 when x is equal to either plus or minus root 1/2. It is negative when x is between these two roots, and is positive when x is greater than root 1/2 or less than root minus 1/2. Okay, now it comes to f. Why it's important? Why these signs are important? Because whenever f prime is positive, that means f is increasing. So when f prime is positive, the function is increasing. So this arrow means f is increasing. Whenever f prime is negative, that means f, the function, is decreasing. Now, when the sign of f prime changes from positive to negative, that point is a maximum or local maximum. So I just put maximum. It makes sense because before x equal to 0, the function is increasing. After x equal to 0, the function is decreasing. So that x equal to 0 is a local maximum because it goes up and then down. So x equal to 0 is a local maximum. But whenever you have decreasing, then increasing, that point would be local minimum. Okay, so this is the max. F double prime. F double prime relates to the concavity of the function. I will tell you what is a concavity. So concavity basically means whenever so if f double prime is positive, the graph of f is concave up. It's like this. Look, it's like this. This is concave up, the graph. If f double prime is positive. If f double prime is negative, it's concave down. It's like this. Concave down, concave up. Okay? So f double prime positive, it's concave up. Oh, wait a moment. Is this minus 2f? Minus 2? But there is a minus sign here. Y double prime is minus. So that means I have to multiply f double prime with a minus sign. Sorry, guys. Because I missed the minus sign before y double prime. You see? There is a minus sign here. So I should put a minus sign here. There is a minus sign. So that means f double prime here is negative, here is positive. Okay. So if f double prime negative, it means it's concave down. Positive, it's concave up. Negative, concave down. If the sign of f double prime switch from negative to positive or from positive to negative, that point is an inflection point. So for example, this point is an inflection point. Inflection point. So this point is also an inflection point. I will show you on a graph so you can see. Okay, now let's see this. on the graph. So here I put all this information together to draw the graph. And also here, because e to the power, what was the function? So y is e to the power minus x squared. So don't forget about horizontal or vertical asymptote. Here we have a horizontal asymptote. Why? Because the limit of e to the power minus x squared, either x goes to plus infinity or minus infinity is 0. So the limit both at infinity and minus infinity is 0. So y equal to 0 is a horizontal asymptote. Let's put everything together in a graph. So x equal to 0 is a local maximum. So what is the value of f at x equal to 0 is 1. E to the power 0 is 1. So imagine this is 1. The limit at infinity is 0. Now, these 2 points, minus root half and plus root half, when x equal to, like, for example, plus root half or minus root half, these 2 points, root 1 over 2 or minus 1 over 2. So these are the inflection points. What does that mean? Inflection point is, you see here, it's concave down. So you see, look at this graph, please. So you see here, it's concave down, but after this point, it's concave up. Concave down, after it's concave up. You see here is concave up, then after this point, it's down, like this. Is that clear or not? I mean, here it's concave down. In this interval, it's concave down. Oh, sorry, I should also correct this because the sign of f double prime is positive. Oh, is it positive or negative? I forgot, I erased. You remember? Do you have f double prime? Here it must be negative. I will compute it again. So f double prime, let me compute f double prime. Y prime is minus 2x e to the power minus x squared. So y double prime is equal to the derivative of this, which is minus 2 times that, x squared, plus the derivative of it, this one, which is minus 2x e to the power minus x squared times the first one. So y double prime is minus 2 times e to the power minus x squared plus 4x squared e to the power minus x squared. So y double prime is e to the power 2 e to the power minus x squared times 2x squared minus 1. So this is y double prime. Okay. Now, based on this, I can tell if x is between these 2 points, it's negative. So this is right. If x is between minus root half and plus root half, then f double prime is negative. And here is positive, here is positive. So that means here is concave down, concave up. So when f double prime is negative, the graph concave down. When f double prime is positive, the graph is concave up. It's like this. You see here, f double prime negative here is concave down. If f double prime positive, it's concave up. So f prime positive is increasing, f prime negative decreasing. Sorry for the confusion. Is that clear? Do you have a question?
Yes, it's clear.
Okay. Good. So let me summarize everything that I told you so far. I mean, maybe it's helpful if I show you some example from the textbook. Do you see my screen?
Yep.
Here you go. Do you see the screen?
Yes, we can see.
Okay, so I told you that how f prime relates to the graph of the function. When f prime is positive, then the function is increasing. For example, look at the figure 1a and b. So f prime positive, the function is increasing. F prime negative, the function is decreasing. But here, what is the difference between a and b? Both of them, the function is increasing, but the difference is the concavity. So the first one, it's concave up, and this relates to the second derivative. If f double prime is positive, it's concave up, like picture A. If double prime is negative, it's concave down. It's picture B. The same for C and D. C and D are both decreasing. So F is decreasing. That means F prime must be negative. Okay. But what is the difference between C and D? In picture C, F is concave, the graph is concave down. So that means F double prime is negative. In picture D, however, F double prime is positive, it's concave up. This is also another picture. So, and here, is an important summary. So it says that if the sign of f double prime changes from positive to negative at the point x equal to c, then f of c is a local maximum. So f prime changes from positive to negative. For example, at this picture, this point, D, x equal to D, so f prime changes from positive to negative, increasing and then decreasing. That would be a local maximum. If f prime changes from negative to positive, that means from decreasing to increasing, then f of c is a local minimum. If f prime doesn't change, so f of c is neither a local minimum nor a local maximum. But that was about the first derivative. How about the second derivative? So it's related to the concavity, points of inflection. So here is an important rule, this theorem. It says that if f double prime is positive, then f is concave up. So in some interval, if f double prime is positive on some interval, then f is concave up. And if f double prime is negative, then f is concave down. So this is an example. So f double prime positive, you see, for x less than a in this picture, look at this picture. If x is less than a, then f double prime is positive. That means f is concave up. For x bigger than a, f double prime is negative. That means f is concave down. So, and when the sign of f double prime changes, either from negative to positive or from positive to negative, doesn't matter, then that point is an inflection point. So in this big picture, x equal to a is an inflection point. Okay? Now, let's draw the graph of a cubic function. For example, let me draw it on a whiteboard for you. Any question? No questions. So let me now draw another function. So this time I want to draw the graph of a cubic function. So a polynomial with degree 3. So f of x is minus x cubed plus 3 x squared.
Bobby,
Yes,
the marker is really hard to see.
is it hard? Okay, I can use my iPad instead. Okay,
Okay.